Hi all, welcome to 7th lecture of Robotics and Controls, and today's topic of discussion is Inverse Kinematics of Differential Drive. Before starting today's lecture, let's discuss what we studied in the previous lecture. Let's recall what we studied. So in our previous lecture, we studied the forward kinematics of differential drive. So um, in that here, so let's say this is the differential drive at t equal to 0, and this is the same robot at t equal to t1. Then we studied how can we find the velocities of the center of mass or the center of this robot xc naught dot and yc naught dot as a function of the wheel velocities. So basically, if we know the wheel velocities or wheel angular velocities, left and right, we can know the velocity of the robot itself. um, so here the expression of the forward kinematics was given as follows. So let's say um, the the velocities were given by xc naught dot, yc naught dot, and theta dot. Theta dot is the angular velocity, which was given by v cos theta, v sin theta, and omega, where v is given by, in terms of wheel angular velocity, is given as 0.5 r, where r is the radius of the wheel, uh, into phi r dot plus phi l dot. These are the angular velocities of left and right and left wheels respectively. And omega is given by 0.5 into r divided by b, where b is the central distance from of the wheels base from the center of the robot, um, and multiplied by phi r dot minus phi l dot. So this was the forward kinematics that we derived in the last lecture, and we also use this forward kinematics equations to write a Python code to trace an L shape by a differential drive robot. And um we plotted the differential drive robot's position by using Euler's method for integration. So in differential drive, the forward kinematics is given as the velocities, and to get the position of the robot you have to integrate these velocities. So for the method of integration we use Euler's method, and we plotted. In today's lecture, we are going to discuss the inverse kinematics of differential drive car, and I have just drawn the diagrams just to reiterate what this diagram represents. So um, this is the position of the robot at t equal to 0. R is the radius of the wheel, and b is the distance of the base of the wheel from the center of the robot. Now there is a coordinate frame x naught, o naught, y naught. This is fixed to the ground. Let's say it's ground frame or fixed frame, and this coordinate frame is fixed with the robot, or it moves with the robot, and so this moves with the robot. This is the position of robot at t equal to t1. The right and the left wheel are rotating by angular velocities phi r dot and phi l dot, and the position of the center of the robot is xc. It can be represented in fixed frame as xc naught comma yc naught. Um, and in the fixed frame, and it can be represented at xc1 comma yc1 in the moving frame. All right, and the robot has rotated by an angle theta and moved to a new point xc naught yc naught. Okay, xc and yc. So um, So what is the goal of today's lectures? What are we going to study in the inverse kinematics? So in inverse kinematics, what we'll take is we'll take a point P. This is P, point P. This is Px. This is Py. All right. And we want to try to this is again Py, this is Px, and this is P. This point is P. So what we want is we want this point P to track a given reference trajectory. That's the goal. So we want this um, P to get a to travel a given reference trajectory. So the goal of the lecture is get the point P to track a given reference trajectory xref and yref. All right, so this is the goal. So why is this inverse kinematics? So in forward kinematics, what we did was we knew phi r dot and phi l dot, and we calculated xc naught dot and xc yc naught dot, right? This was unknown and this was known. In inverse kinematics, what we need to do is we know a reference trajectory of, let's say, xp and yp, and we want to calculate what phi r dot and phi l dot do we need to give as an input to the robot, so that the robot follows this reference trajectory. So let's see how we can do it. So let's say C naught. What's the position of C naught with respect to, this is xc naught and yc naught. How can we write it in terms of C1? So C1 is the position of center of the robot in moving frame 1. So this can be given as R C1 plus D1 naught. So D1 naught is basically the displacement of moving frame 1 with respect to 0. So basically this is the robot at t equal to 0. This is the fixed frame, and this is at t equal to t1. This is the moving frame. Okay, x1, y1. So this is d1 naught. All right, and C is basically this point represented in frame 1. This is C. Right, this point represented in frame 1 is C1. This point represented in frame 0 is C0. And R1 naught is the rotation matrix that is that represent rotation of x1 of the frame 1 with respect to frame 0. All right, so this we calculated earlier. Now this is for the center of the robot. What about this, the point P that we marked, which we want this point, we want to follow this point on a given trajectory. So let's write its a relationship. So P naught equals R1 naught P1 plus D1 naught. All right. So P1 is the representation of point P in frame 1 and P naught in frame 0. So I think this is obvious. Now let's subtract these two. So what we'll get is P naught minus C naught equals to R1 naught P1 minus C1. Alright, so and so this is the relation that we got. Let's try to expand these matrices and vectors. So this can be written as P naught minus C naught can be written as xp naught minus c so xp naught is the position of point P, like x coordinate of point P in frame 0. Alright, so xc naught and y p naught plus y c naught. This has to be equal to R1 naught. If we expand this matrix, this can be written as cos theta, because the frame 1 has rotated by angle theta, right? So cos theta minus sin theta, cos theta. So this is the rotation matrix. And what about the other vector P1 minus C1, which we can write it as xp1 minus xc1 and yp1 minus yc1. Alright, so this is the expanded form of the same. Now we know what this is, right? We marked it in the diagram. So xp1 minus xc1 is what? Let me bring this downwards. Right, so this is the diagram. So we know this is xc comma yc. So xc naught xc1 xp1 minus xc1 is basically this vector, and it never changed because this is point P is fixed to the robot. So this is actually px and py. This quantity is px and py. But in robot frame, all right. This is px and py. So the thing is this so we can write it as xp naught minus xc naught xp yp naught minus yc naught equals cos theta minus sin theta cos theta into px py. All right, so this is the relation. Now let's say you know position of p naught. So let's say given position of p with respect to 0, compute position of c with respect to 0. How can we do that? We just bring this on the other side, like this equation on the other side, this vector on the other side. How will it be? So xc naught yc naught equals xp naught yp naught minus cos theta minus sin theta cos theta. right, multiplied by px py. All right. Now let's say you are given. In other case, it is possible that given position of c naught. So let's say you're given the center of the robot with respect to base frame. You'll have to compute p naught. Let's say the position of point P with respect to base frame. This is a simple. You can shift it to the on the other hand side, and you'll get the relation. So x p naught y p naught can be written, can be given as x c naught y c naught plus cos theta minus sin theta cos theta and px py. Notice the sign has changed. So yeah, so this is the relation. So these two relation, because these are position relation, this will be requiring in the this will be requiring in writing the Python code later. This is not the real inverse kinematics, because inverse kinetics we want to get the relation in the velocities for differential drives. For IK code later. So this piece of information is required for IK code later. We'll see how that goes in the code later on in the lab session. Now we have this equation. Let's differentiate it with respect to time. So differentiate with respect to time. What will happen? Let's differentiate this equation itself. Okay, so what we'll get is x p naught dot y p naught dot equals x c naught dot y c naught dot plus cos so we are differentiating, right? So this will become sine minus sine theta into theta dot. This will become minus cos theta to theta dot. It will become cos theta into theta dot, and this will become sine theta into theta dot minus. Alright. Into, because px and py are constant, so px and py. Alright. Now we can multiply these two, and what we'll get is xp naught dot yp naught dot is equal to c naught dot yc naught dot plus minus sine theta into px theta dot minus cos theta py theta dot. And on the second row, cos theta into px into theta dot minus sine theta into py into theta dot. So this vector can be added to this one. Right. So from forward kinematics, we know that from Fk we know that xc naught dot equals to v cos theta and yc naught dot is equal to v sine theta, right? This we know from fk. We also know that theta dot equals to omega, right? So we can use this interchangeably, theta dot and omega, so no issues with that. But xc naught and yc naught dot can be written as v cos theta and v sin theta. So this is from fk. We discussed it a little while ago in the recall section. So xp naught dot and yp naught dot can be written as v cos theta, v sin theta, and we'll add it also. So we'll add the other matrix with this, and that can be written as minus of px sin theta plus py cos theta into theta naught. Alright, and this can be written as plus px cos theta minus py sin theta into theta naught. Alright, so which can be further written at xp naught dot yp naught dot can be given as this is a vector. It can be distributed as a matrix and vector multiplication. How do we do that? So cos theta and minus px sin theta minus py cos theta. This is one element. This is sin theta and px cos theta minus py sin theta. Alright, this is a matrix multiplied by v and theta dot, which is actually, you can write it as omega, as we saw here, right? So we can write it as omega. Alright, so what is this relation? Can you figure out? So this relation is actually the inverse kinematic relation for differential drive. You got the so we know v and omega can be written in terms of this is not exactly the inverse kinematics, but you know this v and omega can be written in terms of the wheel velocities. So yeah, so we'll use this relation in trying to control the robot in following a reference trajectory. So this is one. Now let's say you have a reference trajectory xref and yref. Xref as a function of time and yref as a function of time. So if you enter the time t, it will give you at what position should the robot be. Okay, what should be the position of point p according to this time. So this is a function. These are two single valued functions. So if you enter the time t, it will give you the position of that point that you want. All right, how do we try to control this? So what we'll now do is try to control the position of point p using a proportional controller. So a proportional controller is what we have not discussed that yet. We'll discuss that in future lectures, but I'll just mention it here, and some of you might have heard about it. So we'll discuss later how does it work and what is a proportional controller, but for now just understand this is a controller which helps the point P to traverse this given reference trajectory xref and yref. All right, so how do we write the proportional controller? So xp naught dot should be equal to some kpx times xref t minus xp naught. So basically this is the position of point P, real position, and this is the position that we want it to be, right? Xref. Okay, so we subtract them, basically the error, and multiply it with the constant k px, and this is, and give it to the velocity. We'll see why this works in later sections, but this is what the proportional controller does. All right, similarly we can write it for yp naught dot equal to kpy yref t minus y yp naught. Okay, all right, so this is the thing. So these position of the position of the point P on the robot comes from sensor measurement, or so for example you might have an encoder on the differential drive robot, or through some odometry you get these positions of position of point P and position of point P in x and y coordinates through with respect to the base frame. So this is the controller to track the, so we call it proportional controller, because the input that we are trying to give is directly proportional to the error. That's why it's called proportional error. So proportional controller to track xref and yref t. All right, so let's call this our second equation. Now let's put, so we know this is xp dot and yp dot, and this is our controller. Okay, now let's put this controller 2 in 1. So put 2 in 1. All right, so if we give this as a controller, what will happen? So we'll place this here, right? So yeah, all right, so k px into xref minus xp naught and y k kpy into y ref function of time into yp naught is equal to let's just copy this. Let me rub the outer box. All right. Let me just rearrange them a little bit. Okay, so this is the resultant thing. You can see this is basically a column vector. We can call this column vector vector b, which is equal to ax. So this is a, and this is our velocity of the robot v and omega. And what we want is so this is basically the input of the robot. So what we want is this input with respect to some given trajectory, right? We want this x with respect to some xref and yref, right? So what we can do is we can send a on the left hand side through inverse. So it will become x is equal to a inverse b a inverse b, and this is the input, and this contains the reference trajectory. So if you want to traverse point P with some xref and yref, the input v and omega you can give is basically a inverse b, where a is this matrix and b is this vector. So it turns out calculating a inverse is really easy here because it is only 2 cross 2 matrix, so we can find it in analytical form. So x equals a inverse b, and a inverse can be given as cos theta minus py by px, you get through from sensors, sin theta, and sin theta plus py by px cos theta, and minus 1 by px sin theta, and 1 by px cos theta. So this is a inverse. So if you multiply this with this vector b, then you'll get the input v and omega, which if you put in the robot, you'll traverse the point P, will traverse the desired trajectory xref and yref. Okay, so this is the inverse kinematics. So basically this equation here is the IK, and now we'll use this calculations to run a Python code in which we want to traverse some point P or the center of the robot through different shapes. Okay, so the first the shape that we want to closely look at is the first shape that we want to look at is asteroid. So it looks like this. So it looks like something like this. So what we want is, we want the robot to travel in this direction, then come here, rotate, travel in this direction, and this direction. This is what we want our robot to do, and we'll use this inverse kinematics. So basically we'll give it the input. So we'll give v comma omega through this IK. Wait. So what? So the way we want to do it is, so we want some trajectory. So IK, some reference trajectory. We call it reference trajectory. Basically we are giving xref comma yref. This is our IK. It will give you what will it give you? It will give you v and omega. So we calculated v and omega from this IK, right? This, so which are inputs, so which can be easily converted to, we have seen earlier, conversion to phi dot r and phi l dot. Alright, so this is what we'll try to implement in the code. For asteroid, the reference trajectory is given by x ref equals let me just mention that it is asteroid is cos cube pi t by 5, and y ref asteroid t is sine cube pi t by 5. Alright, so we want to implement the IK in Python such that the robot follows this trajectory, astro trajectory. Okay, so we'll send this to the IK. It will give us P and omega, which through conversion will get phi r dot and phi l dot, which will send input to the robot, and it will move and hopefully move in this path. So the Python program, we'll discuss in the next video. In the next video, it will be the second part of this lecture, and it has been uploaded as a secondary video. Please go through that. So till the time, thank you. In the next, we'll see you in the next lecture where we implement this Python code. And yeah, thank you.